Well, thank you, Simon, and good evening, everyone. It's great to have the opportunity this evening to, talk to you all about some of the research that I've been doing over the past, say, 3 years or so. Um, as Simon mentioned, I'm a PhD student with Monash University and in collaboration with CSIRO in Melbourne, Australia, as well. And I'll try and be as enthusiastic as I can as you can be at 2 a.m. In the morning about carbon electrodes, but I'll do my best. And so really my research has been looking at perovskite solar cells, including these carbon electrodes, and being able to develop numerous fabrication techniques to make these devices really highly efficient, but also versatile for a whole range of different products. And so let's just dive straight in. So what's our ultimate goal here, and what are we trying to achieve? Well, really, in the end, it looks something like this. So if the internet is streaming nicely, you'll be able to see this nice video of the sequential deposition of our functional layers onto a empty roll of flexible substrate, such as PET, to then pass through from our factory, starting at the start, depositing each of our layers, and then coming out at the other end with our fully functioning solar carpet. Now, those of you with a keen eye will see that this is a video showing the production of organic photovoltaics at the CSIRO's site in Melbourne, where we have a range of different printing facilities. However, this is our current goal for perovskite solar cells. And I'll tell you what, we're not too far off. But really what we're talking about here is transitioning away from our typical means of device fabrication, which is often done via spin coating in our highly controlled inert environments, and progressing towards readily scalable printing and coating techniques, such as slot die coating or gravure coating. Now, the benefit of these is that we can seamlessly integrate these into our roll-to-roll fabrication process, where, as we saw before, we can sequentially deposit each of our functional layers to go from small area cells from the research scale all the way through to larger area modules, interconnected modules, and then progress towards commercial scale products in the end. However, this is much easier said than done. And so all along the way, we face a range of different challenges, starting from moving away from our highly controlled inert environment where we're fabricating these devices in our glove box without the risk of moisture and oxygen degradation. We're then moving towards our ambient lab environment where these molecules play a significant role. We then have different wetting properties between our glass substrate and our flexible PET, for instance. We also have strict annealing time limits and strict annealing temperature limits, which really play a significant influence on the crystallization of our perovskite layer as we're depositing this. Whereas for our glass-based substrates, we might be able to anneal our devices at 150 degrees for 10 minutes. It's a very standard operation. Whereas in our roll-to-roll, our continuous roll-to-roll process, we're really limited to maybe 140 degrees, and we might have seconds, maybe minutes if you're going very slow. And so all of these challenges, again, another challenge there, different solvent drying kinetics, they accumulate. And within the literature, we see a vast difference between the efficiency for these spin-coated devices compared to the roll-to-roll counterparts. And so I'll just bring up one example here just so we can visualize what's actually going on. So his team was able to fabricate really highly efficient devices, 23.5%. This was a few years ago now as well. This was based on ITO glass by spin coating each of our functional layers. However, then by introducing just simply the flexible substrate and the scalable coating process of gravure coating in this case, we see a significant reduction in the power conversion efficiency, all the way down to 13.8% in the end there by roll-to-roll printing each of the functional layers up to the whole transport layer. But as we can see in these devices, they were still all fabricated with evaporated gold electrodes. And so this brings me to my the next challenge that we're trying to tackle, is that despite the advancement of perovskite solar cells being outstanding over the last decade, we're seeing 25, 26% power conversion efficiency, and many teams exhibiting these efficiencies of over 20%. If we take a very close look at these reports, we'll more often than not come across a sentence that goes something like this. So finally, a gold layer was deposited as our counter electrode by thermal evaporation under these high vacuum conditions. And this is the case for almost all of the highest performing perovskite solar cells, where a metal electrode, whether it be gold or silver, is deposited via thermal evaporation. And so whilst this is a very useful technique for our research scale cells in order to create very consistent results, reliable results, and in order for us to optimize each of the other functional layers of our devices, once we start to think about the upscaled fabrication and particularly progressing towards commercialization of this technology, we all know evaporated gold just doesn't fit the bill. And so various other alternative electrodes have been proposed, printed carbon, silver nanowires, even carbon and aluminium foil. But as I showed before, we see another similar trend starting to occur where these teams are able to fabricate highly efficient devices via these traditional methods, but then by introducing these vacuum-free electrodes, so this was a composite carbon electrode, still able to retain the efficiency actually really well, in this case 19.36%, but then by moving to a flexible substrate and then finally upscaling this to a 1 centimeter squared active area device, we again see this dramatic drop in the power conversion efficiency. And so in this case as well, these devices were fabricated via spin coating. And so that brings me to my work. So my work's been focused around how can we tackle these challenges of the upscaled fabrication of perovskite solar cells using carbon-based electrodes, but also retaining that high efficiency as best as we can. And so with that, I want to introduce you to the dry press deposition technique. So we were able to publish this work just last year. And so what we did was we start with the complete roll-to-roll fabrication of our devices up to the HTL. So gravure coating our tin oxide, slot die coating the perovskite, and then slot die coating this spiro as our whole transport layer. We then fabricate our electrode on a separate non-stick release layer substrate. So this is just a PET with, say, a non-stick silica liner. We then firstly coat a silver paste. This can be done using bar coating, as we can see on screen, but it can also be done using screen printing and also slot die coating. We coat the silver paste. We then pass this over a hot plate drying stage, and then similarly coat a carbon paste on top of our annealed silver film before finally passing this over one last hot plate drying stage in order to evaporate any of those harmful solvents that could potentially leach in and degrade our underlying device. We then bring the two together, so our perovskite solar cell up to the HTL and our coated electrode on our release layer substrate, and we simply transfer the electrode. So we're depositing the electrode using compression. So this is done in this case using a calendar press, as we can see on screen here. Following the transfer, we simply peel off the release layer on the other side, exposing our silver film for electrical connection and finalizing the fabrication of our device. And so the main benefit of separating these two fabrication techniques is we're able to mitigate that risk of solvent leaching and also high temperature processing, which you would need to dry these carbon films. And both of these processes can be detrimental to the performance of our perovskite solar cells. And so by using this technique, we're able to achieve some pretty awesome results and demonstrate the world record efficiency for a roll-to-roll printed perovskite solar cell up to HTL with a vacuum-free electrode, achieving a maximum efficiency of 16.7%, which was really exciting achievement for us. But really, what we wanted to do was compare this to devices with evaporated gold electrodes. And so out of the same batch, exact same processing conditions, except with evaporated gold, we were able to achieve maximum efficiency of 17.4%, which not only marked another record for an evaporated gold device, but really what I want to demonstrate here is the direct comparison between the device with our laminated electrode and those with the gold, evaporated gold. This is even better seen once we look at the performance distribution of all the devices in our batch, where despite our evaporated gold exhibiting that exceptional performance for a number of cells there, overall, we get great comparison between the two device types. Now, this device exhibited a stabilized efficiency of about 16%, and then we encapsulated the device using commercial flexible barrier materials, and here's a picture of the device there, and we then subjected it to continuous MPP tracking. This was just a short demonstration, so only 24 hours or so, but we saw no degradation in the device after MPP tracking with our encapsulated cell there. Critically, we also wanted to test the mechanical robustness of these cells, so we can't afford our electrode delaminating from our underlying device under various mechanical loads, particularly once we're looking towards making these flexible perovskite products in the end. So we can see the simple bending apparatus that we have on screen there. You can set your device to either convex or concave bending, and then just track however long you want for. And so we set a 10mm bending radius. This is just in the ambient lab, no encapsulation. And for devices placed under convex bending, so this is with our top electrode in tension there, we see minimal degradation after 3,000 bending cycles. Once we put our devices under concave bending, we do see slightly more degradation under this regime. However, again, once we compare to our evaporated gold, we see almost identical performance drop in these devices, which leads us to conclude that this isn't actually due to degradation of the electrode interface itself, and potentially is one of the other functional layers. And so within this work, we're able to demonstrate, again, some really great results and some really promising results using this lamination technique. However, one clear limitation of using the calendar press is that without significant automation or precise control of that distance between our two calendar press rollers, that slight variations in the thickness of our carbon electrode or of our underlying device stack will lead to variations in the pressure being applied in our lamination process, and subsequently impact the performance. What's more, we wanted to then demonstrate this technique for large scale devices, or larger area devices, it's a better word to say. And with our calendar press there, uneven pressure distribution across the surface area of our carbon electrode will again result in poor performing devices. And finally, we wanted to demonstrate this technique for rigid glass-based cells, which, as you could imagine, would just simply break if we tried to put these through our calendar press. And so I went off and we investigated a range of different other mechanical pressing techniques in order to try and really boost the versatility of this dry press deposition using our bi-layered coated carbon and silver electrode. And we came out the other end investigating cold isostatic pressing. So cold isostatic pressing is typically used for the fabrication of metal alloy rods from base metal powders, where you can apply extremely high but uniformly distributed pressure within your CIP chamber. And as we'll see, it's actually pretty good for the fabrication of perovskite solar cells as well. Now we start off, complete electrode fabrication is exactly the same as what we did before, coating our two pastes onto our non-stick release layer. And in this work, we fabricated devices both on rigid glass, so by our traditional means of spin coating, and also looking at our roll-to-roll fabricated cells as well. And a relatively simple process. So we fabricate these two devices. We then seal them in a vacuum sealed bag before completely submerging the device in our CIP chamber, which is filled with water. We then apply our pressure of say 240 megapascals in this case, and then that transfers the electrode to our underlying spiro hot transport layer. For then we can just pull the device out, peel off our release layer at the end, again exposing our electrode film for electrical connection. And just for a little bit of context here, so for the 240 megapascals, which was our optimized pressure in the end, the time it takes to pressurize our chamber to hold at 240 megapascals for 30 seconds and then depressurize, it takes 3 minutes in total. So only 3 minutes. And the chamber that we're using is a research scale chamber, so 10 centimeter diameter and about 50 centimeter depth. And we can stack that with, we usually did tens of devices at a time, but you could easily go to hundreds or even more. So readily scalable technique. It's also used for industrial applications in terms of large ceramic molds and things like that. Anyway, so this is our final device type. So using tin oxide and spiro as our charge transport layers, similar to what we did in our previous work. And as we found using the calendar press was that establishing a good connection between our carbon electrode and our underlying device stack is absolutely critical in obtaining high performance. Now, this was systematically shown using the CIP by varying the pressure, starting at 35 megapascals, where under the SEM we were able to see large areas of delamination between our carbon electrode and our underlying device. Once we then progress to 100 megapascals, we see much better connection at this interface. But if we look closely, you can still see small cavities at this critical interface between our carbon and spiro, therefore resulting in that lower charge extraction and lower efficiency. Finally, 240 megapascals, really immense pressure, but we were able to see this seamless connection between our carbon and underlying spiro, which if we look at the normalized power conversion efficiency, we're able to see results in our highest performing devices there. And we see this again, just a couple of little videos here just to show 15 megapascals too low. The electrode peels off very easily. 100 megapascals, we get better connection, but if you do some destructive analysis, you can very easily peel off the electrode. And then 240 megapascals, this was for a carbon only electrode. You can very easily peel off the release layer and it's stuck very well. So it's actually very hard to delaminate from the device without actually completely destroying the underlying layers as well. If we look at the electrodes under the SEM, we see we do get slight compression of the electrodes going from about 50 micron to 40 for our carbon and about 35 to 30, maybe a little bit less for our silver. Now this was shown to also improve the conductivity of our electrode film. Interestingly, the carbon film actually reduced in conductivity, but the silver film significantly improved in terms of electrical conductivity, which then led to almost twice the conductivity with our pressed electrode. All of this then translated into achieving some really great results on the research scale. So for 0.16 centimeter squared cells, we were able to directly match the performance of our evaporated gold counterparts, achieving a maximum efficiency of 20.8%. Now this was the maximum for both our laminated electrode and our evaporated gold after batches. So batch after batch after batch, these were the maximum efficiencies we were able to achieve. This device exhibited a stabilized efficiency of 20.3%. And again, if we look at the devices in the batch, we can see, again, a great comparison between our laminated electrodes and our evaporated gold. We see that the major difference is due to a drop in the JSC, which we attribute to a lack of back reflection from our carbon electrode in comparison to the highly reflective gold electrode, which allows for that secondary light absorption. And then once we compare to all the devices in the literature, so this is showing devices with carbon-based electrodes, so monolithic devices with carbon-based electrodes, we see that we're right up there on this research scale cell area. So around 0.1 centimeter squared, we're right up there with the best. And we could almost say we've achieved a record for low temperature fabricated devices if you look at that temperature bar over on the right-hand side there. But what we also see from this graph is that there's a significant drop in the power conversion efficiency once we tend towards larger area cells. So cells of 1 centimeter squared and above, we see a substantial drop going from 20% down to about 17%. Now, this is typically due to the low conductivity of carbon electrodes, which is then exacerbated at this larger cell areas. But what's more, it's also due to the poor interface connection between the carbon electrode and the underlying device stack once teams progress to these larger cell areas. However, the benefit of our bilayer electrode design is having the highly conductive silver film. And what's more, with the immense pressure that we are applying with the CIP, we then progressed to developing these larger area cells to see how they would fare against the literature. And so simply, devices fabricated exact same as before by simply cutting larger electrodes to fit the device size. And we were able to push these limits really and achieve up to 19.8% for a 0.95 centimeter squared cell and 16.9% for a 5.5 centimeter squared cell. Now, all these devices exhibited good stabilized efficiency. And really, we can see the benefit of the CIP here in applying uniformly distributed pressure across the whole surface area of our electrode, which, as we can see by the photocurrent map, then results in uniform photocurrent generation, again, across the whole surface area of our device. And if I bring up this graph just one more time, what we're able to see is we were able to smash the record for cell areas of roughly 1 centimeter squared and pushing even further into the area really of no man's land. There's only been a number of reports there. We've been able to demonstrate these efficient devices at this level as well. But efficiency isn't everything. We all know that. We all know efficiency isn't everything. We also need to take into account the stability. And so throughout the literature, carbon-based electrodes have exhibited better stabilized efficiency compared to evaporated gold. And so we undertook a range of different tests just to see if ours would fare the same way. And what we're able to see is actually under storage, both the electrode types exhibited similar efficiency. So this is after 1,000 hours and 1,600 hours storage in nitrogen and ambient. And yeah, there's not a huge difference. I mean, we can see the carbon electrode maybe slightly outperforms the evaporated gold in ambient storage, but really overall, there's not a huge difference. However, once we then progress to continuous illumination, accelerated operational conditions, that's where we were able to see a significant difference in terms of the stability performance. So this is in a low humidity environment, 10% relative humidity, 30 degrees, and continuous MPP tracking. And so over 1,000 hours, we can clearly see there that the evaporated gold cell rapidly degraded. And within 10, 20 hours, it had lost a significant amount of its efficiency. And after 200 hours, it had dropped substantially. If we normalize this, taking into account the consensus that was published in 2020, looking at the stabilized efficiency, we're able to calculate the T80 lifetime of these cells of just over 1,200 hours. So these are for unencapsulated devices as well, which we can see is 100%, 100 times improvement. So 2 orders of magnitude improvement comparing our evaporated gold to the laminated carbon and silver electrode. And then just finally, looking at the versatility of this technique. So not only were we able to fabricate devices with that were fabricated on rigid glass-based substrates, we were also able to use the CIP technique to fabricate devices, the roll-to-roll fabricated devices, as I was talking about before. And we're able to achieve efficiencies of up to 15.8% so far, but we believe we can push this even further. And really the benefit of this technique is that we can seal a whole roll of devices, completely submerge this in our CIP chamber, and then apply the uniform pressure. And we know we're going to get reliable and quantifiable pressure at each of those cells along our batch, which is a huge advantage. Furthermore, we were able to demonstrate bespoke cell designs. And so looking towards commercialization or some sort of product design, we were able to demonstrate that the isostatic press, we can achieve this uniform pressure distribution looking at these custom electrodes, as we can see on screen. And then finally, just on the bottom right hand side, just a picture of all the devices, device types we were able to fabricate. And really the possibilities keep extending further than this as well. Obviously acknowledgement, so this all can't be just due to me. So huge shout out to the whole team at CSIRO, the Flexible Electronics Lab. If you don't know about them, look them up. That we do some awesome stuff, and within the next 6 months, we're going to be releasing some more awesome work and really pushing the limits of particularly these roll-to-roll fabricated perovskite solar cells. So keep your eyes and ears out. And also to the people at Monash Uni, particularly my supervisor, George, for helping me throughout this process, and to the Australia-India Strategic Research Fund for being the main funding body of this work. And I want to thank you, and happy to open up for questions and discussion. Thanks.